Hi everyone, welcome to the chapter number 4 from Unit 3. So in this particular chapter we are going to discuss about the bipolar junction transistor, okay, BJT. So we'll see the bipolar junction transistor introduction. So in case this particular bipolar junction transistor, that is a transistor, is invented by the three scientists, okay, three scientists in the Bell laboratory, at Bell laboratory. So here the country is a USA. USA country, which year it is invented 1947. So and at 1947, three scientists from the USA Bell Laboratory they invented the bipolar junction transistor. Before that we are using the vacuum tubes instead of bipolar junction transistor. Once you invented the bipolar junction transistor, total entire electronics is drastically changes. And then now we will see ICs, integrated circuits, everything. Nanotechnology is also coming to. It is invention from the BJT, bipolar junction transistor. The step by step generation will be developed. So now there are two basic type of transistors. So what are the basic type of transistors we have? The first one is a BJT, bipolar junction transistor. The second one is a field effect transistor. So there are two types of transistors. We are going to discuss BJT, bipolar junction transistor, in this particular chapter. And then chapter number unit 4, chapter number 3, I guess, field effect transistor, will discuss their complete details about that. So now this particular bipolar junction transistor, to form two diodes connected back to back, it forms a connected back to back two PN junctions. So manufacturing the single unit, it forms a transistor. Now it consists of a three layers and three terminals device, three layer three terminal device. It is also important. So BJT is how many layer? Three layers, three terminals, two junctions. Very important. Two junction device. Three layer, two terminal, two junction devices. So what are the terminals we have? Emitter. So look at here. So in this particular diagram, it shows the transistor symbol. The transistor is having emitter, base, and then collector. There are two types of transistors we have. The first one is a two p-type material sandwiched with in between sandwich with n-type material. So inserted in between the n-type material, this is a PNP transistor. So this is a symbol for PNP transistor. This arrow, it is indicated towards the base. That means that this emitter terminal is more positive compared to the base and collector terminal. That is indication. After that, PNP transistor, the two n-type materials sandwiched with the p-type material, it is a NPN transistor. This is the representation for NPN transistor. The current will be entering to the emitter. It means that emitter is with respect to emitter is a negative, more negative. So base and collector is more positive with respect to the emitter. That is indication for this particular arrow. Okay. Now this particular case, the arrow represented the conventional current. This particular arrow is represented the conventional current, that is the opposite flow of electrons. Okay, the arrow is indicated that flowing of electrons in the opposite direction. So conventional current, it is arrow direction. So we have a two junctions are there, already mentioned. What are the junction? This is the first junction, this is the second junction. That is a emitter base junction. That is a junction 1. Junction 2 is a base collector junction. That is a junction 2. Okay, two junctions we have. So in the both the cases, NPN and PNP transistor, we have a two junctions, emitter base junction and as well as collector base junctions. So we'll discuss one by one. Emitter. What I mentioned, every point is important in the case of examinations. Everyone listen carefully. It is a transistor is maximum students are feel difficult transistors, and field effect transistors are very very difficult, like that in case of electrical students, even though some electronic students also. So if you are listening this particular classes what I am explaining, transistors are very very simple. Field effect transistor, total entire EDC is also very very simple. In the KVS TGT, more than 50% marks is coming from this particular unit 3 and unit 4. Okay, so what you prepare still now, unit 1, unit 3 and unit 5 we completed, right? So 50% marks, remaining unit 3 and unit 4 having 50%, remaining 50% marks coming from this. So everyone concentrate and listen. So okay, emitter. So the first point you need to remember, emitter is a heavily doped compared to remaining two. So the first point you need to remember, emitter is a heavily doped. So then you will get the doubt why it is heavily doped, because emitter itself, it emits the majority charge carriers, it supplies the majority charge carriers to the base and collector. So whenever it is supposed to supply the majority charge carriers to the base and collector, is supposed to heavily doped. Whenever it is heavily doped, it is able to supply the majority charge carriers. So it supplies majority charge carriers. Okay, that is the second point you need to remember. So you know, the majority charge carriers may be either electrons or holes. In case of NPN transistor, you know, electrons is a majority charge carriers. In case of PNP transistor, holes is a majority charge carriers. Okay, now another second terminal is a base terminal. So base one. So coming to the base, you know, it is a middle section. Already you see, this is a middle section, this is a base. So it is a middle section. It is a very thin. The first point you need to remember, it is a very thin layer compared to emitter and collector layers. It is a very thin. It is around 10 power minus 6 m. Okay, meters, minus 6 meters. So compared to the either emitter and collector, but it is a lightly doped. It is a lightly doped. Okay, it is a lightly doped. So this is about the base. Coming to the collector. In case of collector, it is a moderately doped. It is a moderately doped. But the thing you need to remember, the collector is collect the charges. So collect the majority charge carriers. Collect the majority charge carriers. So if you want to collect the more majority charge carriers, how to design this particular layer? It is a particular layer is a physically larger. So this particular layer is a physically larger. Why it is a physically larger? Because compared to emitter emits the electrons, base it is flowing from the base and then it is collector able to collect the electrons. That's why the layer width, I'm talking about the layer width is more in case of transistor compared to the width of base and emitter. Got my point? The collector width is high, but it is a moderately doped. Emitter width is a moderate, but doping is heavily doped, emitter. So these points are basic points. So if you want to understand properly totally every concept related to the transistors, we need to understand these particular concepts. Clear about all these three terminals, emitter, base and collector. So my question here, it is a possibility there interchange the emitter and collector terminals? No, because the physical requirements for the emitter and base, emitter and collectors are physically it is a large layer. In case of collector, if you are interchange, so it going to be affected on the working of the particular transistor. So can't interchange emitter and collector terminals because of this physical structure. Next we are moving to the transistors. Okay, transistor biasing. You know, biasing itself is nothing but a supply. Biasing is not any new term. Biasing is nothing but a giving input supply, that is called as a biasing. So we will see how exactly the bias the particular transistor in the both the case of PNP and NPN transistor. So look at here first PNP transistor. So the the proper working of transistor. So essentially, apply voltage with correct polarity across the two junctions. Then only it is a properly biased. For that case, you need to remember two cases: emitter base junction. So this is the emitter, this is the base junction. In case of PNP transistor, so positive terminal should be connected because emitter base junction should be forward bias. Every word very important. Emitter base junction should be forward bias. That's why plus terminal is connected to P type material. Next, second point, base and collector. So the second point, collector and base, that is a CB junction, is reverse bias always to operated transistor in the active region. So I will tell you the remaining things: active region, cutoff region, and saturation region. Some other cases. Now we are going to discuss about the active region only. Now the base and collector junction should be reverse bias. Okay, clear? These 2 points have to remember to connect the particular polarities to the transistor. So if it is a reverse bias, negative terminal connected to the P type material, then it is a reverse bias. So input junction is a forward bias, output junction is a reverse bias. So that's why it is called as a transistor biasing in the forward direction, forward biasing. After that, we have a two supplies, plus VVE and then VCC. This is a collector voltage, this is the emitter to base voltage and collector to base voltage, VCC. Now in case already mentioned the polarities and everything, coming to the NPN transistor. In the NPN transistor, emitter and base junction should be forward bias. That's why how it is forward bias, negative terminal is connected to N type material, then it is a forward bias. That's why negative and positive connected in the input, as well as it should be reverse bias. Whenever it is reverse bias, N terminal connected to plus, then only it is reverse bias. Yes or no? Yes, that's why it is connected plus and minus. So the current directions. So in case of NPN transistor, this is a current direction. Emitter, the current will be delivering flows towards the emitter. So towards the base. That means that the current here and the current via IE is equal to IC plus IB. We'll discuss in the later. Here also IE is equal to IC plus IB. Current delivering from the emitter. Going from the emitter, we'll discuss the current directions later. Another important point. So whenever it is connected positive terminal, that means that this positive terminal attracts more electrons towards the P type material, towards the emitter. Okay, in this particular case, this negative terminal, it attracts more holes from the base and collector towards the emitter. This negative sign, that means repel or pull or attracted opposite polarities of particular majority and minority charge carriers. Once again, I will repeat for your understanding purpose. You should understand everyone. So see here. Whenever it is connected positive sign, so this positive sign connected here, more number of holes are present in the P type. Majority charge carriers are holes. These holes have a positive polarity. Whenever it is biasing, this is a polarity. Even there is no power supply, there is no polarity at all. Now, whenever it is a more positive, majority charge carriers are repelled by this polarity, positive. Whenever it is repelled, so some holes are trying to form towards the junction, the N type, towards the base. It is trying to flow towards the base. What about the negative electron? What are the majority charge carriers in the base junction? That is the electrons trying to attract out from this positive terminal. That means that recombination of electron hole pair is taking place. Recombination of electrons whole pair is taking place, and then whatever the free electrons are, those electrons are cross over this particular barrier, particular junction, trying to flow. Okay, this is the way in the N-type material also. I hope that you got idea about why you are connected positive for the input side, why you are connected negative in the output side in the case of PNP transistor. So next we are moving to the important biasing rules. So how the biasing exactly, what are the rules behind that, we'll see. So biasing rules, in that particular case, this is a PNP transistor. In the PNP transistor, so the biasing we can represent two negative terminals. Okay, it is represented one positive terminal. So how the positive or negative terminal, how can you identify that? In case of PNP transistor, so you should remember N is present. That nothing but a emitter as well as collector. Emitter as well as, okay, we'll see how the polarities will be represented, important biasing rules. In case of PNP transistor, with respect to emitter, base and collector is a negative. Here N is there now. With respect to emitter, base and collector will be negative. So how the base, but collector is more negative compared to base, that's why it is represented 2 minus signs. Got my point? Why are represented two minus sign there? It is a representation that B terminal compared to B terminal, C terminal is more negative. So with respect to E terminal. This is about PNP transistor. In case of NPN transistor, we'll see in the NPN transistor, P type, that is a positive. P, I'm giving the shortcut. Here N is there. N is nothing but a negative. Both collector and base are negative. In case of PNP transistor, middle term is P. P means positive, you can identify that shortcut. So that means that collector and base are positive with respect to emitter. Collector and base are positive because P terminal is there, NPN. P is a positive. You remember, collector and base is a positive with respect to emitter. So that is about here two pluses are represented. Whenever two pluses are represented, compared to the base, collector is more positive. Collector is a more positive. That's why it is a plus and plus. Two plus symbols are represented. Same diagrams are written here, but the notations are here. The voltage between these two terminals VBC. Okay, the voltage between these two terminals VEB. Got my point? Next, don't call it as a VCB here, because which one is a less positive, less negative? B. That's why less negative terminal should be right first. Once again I will repeat, while you are writing the voltage between B and C, don't write it as a VCB. That is wrong. We can write it as a VBC. Why? Because here negative terminal is a one terminal, here two terminals are negative. Less positive is B. That's why B terminal should be write first. Coming to here, VEB. E is positive compared to B, because it is negative, it is positive. That's why VEB, not VBE. Right? It is wrong. It is represented in its correct VEB. Got my point? And similarly, all the cases, which one is a positive, more positive, you can take it as a first letter for that. That is another rule we have to remember. So this is about the biasing rules in this case of transistors. Okay. Input is always forward bias, output junction is always reverse bias. So next we are moving to the transistor currents. Very, very important. Everyone have to understand this particular concept. So in the transistor currents, so we'll look at the two cases, NPN as well as PNP transistor. First we'll look at the PNP transistor. In the PNP transistor, current entering to the emitter current entering into the P-type layer, that is emitter current is towards the transistor. So always towards the transistor we can consider as a positive, towards current flowing towards transistor. Okay, current away, for example this current is away from the transistor, we can consider as a negative, away to the transistor. So here also base is also away. So whenever you are given the emitter emits the majority charge carriers are 100%, for example. Whenever it is emits the 100% charge carriers, it is trying to flow, but emitter is a thin layer. Emitter is a thin layer, lightly doped. That means that very small current will be flowing through that is a 2% is flowing through the base, and then remaining 98% flowing through the collector. Got my point? That means that this emitter and collector current approximately only 2% is different. That ratio you need to find out. We'll see in the later cases, in the common base, common emitter and common collector configuration. I will explain clearly, but you need to understand this is a thing happened. Okay, now it is particular circuit is converted into like a transistor configuration. So emitter current, for example, this is a common base configuration. This is a common base configuration. For example, you are taken as a common collector. So common emitter configuration, emitter is connected as a common to the input and output. In that particular case, 100% is given. Again, the current will be flowing 2% here. The current will be flowing 98% here. Emitter, here see, base and emitter should be forward bias. That's why it is a N type. That's why negative is connected here. And then it is a reverse bias. It is a P type. That's why negative is connected here. It is a reverse bias junction. It is a forward bias junction. That condition should be satisfied. Now, the consideration of currents here, the current IE, emitter current, is equal to the combination of collector current plus base current. This is valid for both NPN and PNP transistor. Always this particular case is valid in the both the cases, NPN as well as PNP transistor. I hope that everyone is clear about the transistor currents. The transistor currents in either it is NPN transistor or PNP transistor, the transistor current, emitter current, is equal to IC plus IB. Okay, I don't want to repeat once again NPN transistor. The same thing is happened for the reverse current directions are reversed, but the equation is same. IE is equal to IC plus IB. Okay, then we are moving to the summing up. Okay, summing up means, so we have a three cases here. First one is what are the current we are consider the conventional current flow only. Okay, what are the currents we are going to take? Conventional currents only. So the first point here, conventional currents. So the arrow, particular arrow represented the conventional currents. And then the second point you need to remember, emitter base junction, that is the input junction, always forward bias. And then third one, collector base junction, always reverse bias. These 3 points. The fourth one is emitter current is equal to, irrespective of ENP or NPN transistor, base current plus collector current. This is about the things we need to remember. In the next class, we are going to discuss about the transistor configurations as well as leakage current and thermal runaway. Then we will going to end up this particular chapter. Okay, thank you.